Chevette and Connor happen to live right beside each other. It happens to be a Tuesday morning. We've had beautiful weather for 2.5 months, but they wake up Tuesday morning in the houses that are right beside each other, 6 o'clock in the morning, look out the window, there's 73 centimeters of snow on the ground. They live right beside each other. They both have identical driveways, same width, same length, because they're on the same street. They live right beside each other. They both have exactly the same amount of snow in their driveway. Good news is, it's a snow day, no school, because there's 73 centimeters of snow. The bad news is, Mom says you got to shovel the driveway. So they both happen to go outside, out their front doors, at exactly the same time, at 9:01 a.m. Now, there's a lot of snow in the driveway, right? It's a 20-foot wide driveway, and there's 73 centimeters of snow there. It takes Chevette an hour and a half to shovel that driveway. Okay, that's a long time, but there's a lot of snow in the driveway. Connor takes him 4.5 hours to shovel his driveway, even though his driveway is exactly the same as Chevette's. Here's a quick question for you. Who did more work? Connor, who worked for 4.5 hours shoveling the same driveway, or Chevette, who worked for 1.5 hours shoveling the same driveway? In other words, what I'm asking you, is it more work to do it quicker, or is it more work to take your time and do it slowly? What do you say there, Matt? Who says the same amount of work? Who says Chevette did more work because she did it quicker? Who says that Connor did more work because he worked for longer? Okay, so a couple people, Chevette, a couple people, Connor, and more people saying they both did the same amount of work. Well, the reality is they both did do the same amount of work. Here's the deal. You're trying to hire someone to shovel your driveway. If you're going to pay them by the amount of work that they do, not by how quickly they do it, but just simply by the amount of work that they do, then you're going to pay them the same amount. Because in the end, Chevette shovels their driveway, Connor shovels his driveway. They both do the same thing. They both did the same thing. The work done is the same. Think about it this way. It takes Connor about the same amount of energy expended to shovel his driveway as does Chevette. Chevette is just able to expend that energy a little bit quicker. That's all. If you think about force versus displacement, well, on average, the force that Chevette applied and the displacement over which she applied it, on average, was the same as Connor's, just that she was quicker, 3 times quicker than Connor in doing it. So the work done is the same. If you're paying them by the amount of work that they do, you're going to pay them the exact same amount. But what if you're hiring them based on how quickly they do it? You're going to pay them an hourly wage. Well, you're going to hire Chevette then, right? Because Chevette is 3 times as quick doing it. How do we quantify that? It can't be work because they've both done the same amount of work. We're going to quantify that based on a new term called power. Power is the rate at which work is done. Not how much work is done, because 2 people can do the same amount of work, but clearly have different power outputs. Power is the rate, how quickly the work is done. You got to have some way of quantifying how quickly you do work. Going to be power. Now power, given by the symbol capital P, not a lowercase p. Next year you're going to learn about momentum, which is a lowercase p. Okay, power is a capital P, and it's a scalar, is equal to work. It's the rate at which work is done. Work over time. Anything that's a rate has time on the bottom. We could also, by the way, write it like this if we wanted to. Power is equal to delta E over T, because work is equal to the change in energy. Now, what do you think the units would be for power? What units do we use for power? Yeah, joules per second, right? Energy over, or work over time, joules per second. But there's another set of units that that we can shorten this up with a little bit. Okay, instead of calling it a joule per second, we can simplify a joule per second into one other variable. What do you think that one other variable might be? What do you think the units for that would be equivalent to a joule per second is? I'm trying to give you a hint here, okay? What would those units be? McKenna? The watt, right? It's a watt. We abbreviate that with a capital W. Be careful. Work is in joules, but its symbol is W. Watts are the units for power, and its symbol is W. So don't get mixed up between the work done here and the units for power right here, which is the watt, the joule per second. This is a variable that we have right here. This is a unit that we have right here. So although they look the same, it's two different things. We're going to do an example, but the example we're going to do is a little bit different than the one that we usually do when we introduce a new topic. The example problem that we're going to do today is a little bit of an activity. It's going to go pretty quickly for us, and the good news is we're not going to have to write anything up for this. You're going to find the power output of your legs. And you're going to find the power output, how quickly your legs can do work. Now, we're not necessarily looking for the maximum power output of your legs. Okay, if you want to find the maximum power output of your legs, then you need to work as quickly with your legs as you can. If you just want to find the power output of your legs on any given normal day when you're walking around, then just walk. Here's the deal. You're going to go out into one of the two stairwells that kind of go up and around, right? The one that goes up to Mr. Crawford's lab up here, and the one that's outside of the wood shop down there. Don't go to the one down by the gym, because that goes straight up all the way. I don't know what the height of those stairs are. You're going to go to this one, or you're going to go to the one down by the wood shop. And you know that as you go up those stairs, there comes a point when you turn and then go up a few more stairs in the opposite direction. Okay, when you make that turn, you stop. Okay, that's your climb. That climb is 3 meters high. So you're going to walk up those stairs, you're going to run up those stairs, whatever it is, height of 3 meters. You're going to need your mass in kilograms. If you know your mass in kilograms already, that's great. If you know your mass in pounds already, you're going to divide that by 2.2 to get kilograms. You need to know gravity, 9.81 meters per second squared. And you're going to need to know how long it takes you to go up those stairs. This is what you're going to measure out in the stairwell. Okay, you're either going to walk up those stairs or you're going to run up those stairs, and you're going to time how long it takes you yourself to go up those stairs. So just before you begin to go, until to the point when you get both feet up, both legs up to the top of the stairs. Measure how much that time is in seconds. Now, you're going to find your power output, which is work over time. But the work is equal to the change in energy, right? Delta E. What kind of energy do you have once you're at the top of the stairs? Good, mgh, potential. What kind of energy do you have before you started at the bottom of the stairs? None. So your work done is equal to your change in potential energy. However much potential energy you gain as you run up those stairs or walk up those stairs, whatever the case may be, is equal to your work done. You're going to divide that by the time that it took you to go up those stairs, and you're going to get your power output in joules per second or in watts. Sorry, you're right. A little typo there. That should be mgh final, not mgh initial. Our initial height would be 0, right?